Hey there, we're going to look at two pretty simple, what I call parent functions. And the reason I call these parent functions is because they're really basic functions without a lot of extra arithmetic or transformations. So no transformations in this video, just parent functions for absolute value and power functions. Let's get going. So the first thing is, what am I defining as a parent function? So for me, um, generally speaking, a parent function can really be any function, but uh, what I'm looking at is a function with one, and I'll call it higher order operation on X, on the input. So when I say higher order operation, I mean not arithmetic, not your basic arithmetic, not addition, subtraction, multiplication, or division. Okay, so the operations we're going to be looking at here are absolute values and powers. And so let's get started. You'll see I've got graph paper here on my screen. If you're taking notes, I recommend using graph paper to make your life a little bit easier. Uh, but for my purposes, I want to make a decent video. So let's graph f of x, or let's call it y. Let's just make it simple. Let's just say graph y equals the absolute value of x. This is the parent absolute value function. The parent absolute value function. There are versions of this absolute value function that have addition, subtraction, multiplication, or division. Those require transformations. A parent function has no transformations for my purposes for this video. So how would you graph this? And this is something you should be able to graph really quickly. And the idea is you should be able to generate an XY table for this in 3 or 4 seconds. And the idea is with one operation, one higher order operation like absolute value, it's really easy to calculate the outputs. Now, the domain of this function is just an absolute value. So the domain of this function, x, can be anything. Okay, so that's our domain, any real number. So you want to include some negative numbers, 0, and some positive numbers. So I'm gonna start on the negative side, and you can choose any negative number you want. So I'm gonna say dot dot dot, indicating to go all the way back to negative infinity. But maybe I'll do -3, -2, -1, and then 0, and then the positives 1, 2, and 3. No problem. That took like 1 second to write. And now to get the outputs of those, the y values here are determined by the formula. Well, y is the absolute value of the x value. So it turns all of the x values to positives when you do your y's. And that's it. That's our table. So what does the graph of this look like? So the graph, I'm going to start in the middle here. This 0, 0 is right in the middle. I'm going to call that a reference point. Okay, a reference point. So 0, 0 is right here. And let's assume a scale of 1 in each direction. I'll do the positive side first. So 1, 1 is there, 2, 2, 3, 3. What you get on this side is a straight line. If you keep going, you get a straight line like this with a slope of 1. And if I look at the negative side, if I go to -1, +1, that's here, -2, +2, -3, +3, I get another straight line. So the absolute value function has this V shape. So the absolute value function has a V shape, okay? And that's it. That is the parent absolute value function. Should be able to generate that very quickly and generate multiple points on the graph. Another thing I'll mention is that this function is what we call an even function. An even function. What is an even function? Well, an even function is where f of -x, if you plug in some negative x value, is the same thing as if you plugged in the positive x value. So for example here, you can see that the f of -3 is 3, and f of +3 is also 3. The negative x value has the same output as the positive x value. And what you'll notice is those correspond to these 2 points here. So these 2 points are symmetric over the y-axis. So an even function says f of an input is equal to f of the opposite input, and it also means it's symmetric over the y-axis. So the absolute value parent function is an even function. Let's start looking at the power functions. A power function is x to a power. So if I graph y equals x squared, this is a quadratic parent function. So this is a quadratic parent function, but it's a power function. A power function can have any power on it. And again, the idea is one operation on x. You're just squaring the x values to get the y value. So when you look at the table, again, x can be anything. So you want to think negatives, 0, and positives. And then the y values here are simply the x values squared. So we get 9, 4, 1, 0, 1, 4, 9. See how easy that is? And again, we get 0, 0 in the middle. Let's see what the graph looks like. Again, I'll assume a scale of 1 in each direction. So I'll start at the reference point, 0, 0, right here. And look at the positive side, 1, 1, 2, 4, and 3, 5, 6, 7, 8, 9. So this side is not a straight line now, it curves. Let's look at the negative side, -1, 1, -2, 4, -3, 9, and it's a mirror image over the y-axis, like this. So it's not a V shape like the absolute value, it's not 2 lines, but it's now more like a U shape. Okay, and you'll notice that this is symmetric over the y-axis, so this is also an even function. And this is also similar to y equals x to any even power. If you graph y equals x to the fourth, it's very similar. It's going to be a U shape. It's just going to be steeper. As the power gets higher, it gets steeper, as long as it's an even power. So let's look at the remaining power functions, y equals x to the third power and odd powers. So let's graph y equals x cubed. This is the cubic parent function. And again, x here can be anything. Any real number. So we'll have the same x values, some negatives, 0, and some positives. And the y values here are the x values to the third power. So -3 times itself 3 times is -27. -2 to the third power is -8. -1 to the third power is -1. We get 0, 1, 8, and 27. Okay, and again, our reference point here, our middle point, if you will, is 0, 0. So now I'm going to start with our reference point 0, 0, which is right here, and I'll do the positive side first. So 1, 1, 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. And then 327 is way up there. So this side is curving and growing, much like the x squared function, but it's growing faster. So again, the higher power means faster growth. Let's look at the left side. If x is -1, y is -1, then we get -2, -8. 1, 2, 3, 4, 5, 6, 7, 8, and then -3, -27 is way down there. So it grows rapidly, but in the negative direction. So this is your cubic parent function. Notice that this is not symmetric over the y-axis, but what it is, it's symmetric over the origin. This point and this point are symmetric through the origin, okay? So that's what we call an odd function. You'll notice that the output for -3 is -27, and the output for +3 is +27. The outputs are not the same, they're very similar. They are opposites of each other. And the definition of an odd function says that f of -x is not equal to f of x like an even function, but it's equal to the opposite of f of x. And an odd function has symmetry over the origin. Okay, so this is an example of an odd function. And it makes sense, it's an odd power. Not all x cubed functions are symmetric over the origin. So they're not all odd, even though they have an odd power, because they may not all be symmetric over the origin. And this is similar to y equals x to any odd power. Like x to the fifth is very similar, just grows faster in both directions. The only one that's not like this is if it's x to the first power. So really we want an odd power greater than 1. X to the first power is just a straight line, okay? All right, those are the parent, absolute value, and power functions. Should be able to generate those XY tables and graphs very quickly. And I hope that made sense about even and odd functions as well.